So last time we started on section 3.1, which is Numeration Systems, and we were in the middle of talking about our friends the Mayans. So just to remind you where we were, since we're sort of in the middle of their system, they have three symbols in their system: a dot, a horizontal line, and this shell shape. 1 is the value of the dot, 5 for the line, and 0 for the shell. They have this modified base 20 system where they have the ones place, the 20s place, and then the 20 times 18, 20 squared times 18, and so forth. Their lowest values on the bottom, the highest value in their numbers on the top. And typically within a place value system, what we see written, like with the norm, is that the dots are supposed to go in front of the lines. And so if you see the reverse happen, then it automatically means that there's a change in place value. So you saw that happen on this orange one where there's a line between. So our example that we are on is example 6, and we're actually going to go in reverse now. So we're going to take a value in their system, and we're going to turn it back into our number. Now we did this with the Babylonians last time, and it looked like this division algorithm. Okay, I know it's been 2 days since you've seen it, but does anybody vaguely remember this division algorithm? So in order to do this division algorithm, you have to know the place values that you're going to be dividing by, right? These are our place values here in yellow. And over for our Mayans, these are actually our place values. We already calculated them last time, so they're the ones that we're going to be using for our division algorithm this time. So our number is 58,000, which means the biggest place value that we need to divide by is actually which one? Which one? The one with the square, the 7,200, right? Yeah. So we're going to divide first. I'll write them down on this screen so that we don't have to keep flipping back and forth. It was 7,200, 360, 20, and 1. Those are the values. And I've put them sort of in hierarchy from the top to bottom like that because eventually our number is going to have to be written in that vertical form because that's their system. So the first thing we're going to do is we're going to divide by 7,200. And our number is 58,532. Like so. It's a little small, isn't it? Make that just a little bit bigger for us. All right, so how many times will 7,200 go into 58,532? Your calculator is going to be your friend on this, so make sure and grab it out. You'll need it. How many times will it go in? 8. Yeah, it's 8. Okay, and then we need to do 8 times that 7,200. So what is 8 times 7,200? Or 7,200?
57,600.
Very good. And then we subtract and we continue. So what is our subtracted value giving us? All right, so we divided by the 7,200. Now we're going to divide by 360. It's the next place value. So how many times will 360 go into 932? It's 2. 2 times 360, you might be able to do that one in your head, or think about that one, that's 720. And if I subtract, what do I get this time? 212, good. What's my next value to divide by? It's 20. So how many times will 20 go into 212? 10. Yeah, you probably could see that one. So that's 200. And if I subtract, I have 12. And then my last step is always division by 1. 1 goes into 12 12 times to give me a 0 at the end. Okay, so everybody good so far? Wonderful. So what we're wanting to do then with the 8, 2, 10, 12 is we're wanting to write those in the symbols from the Mayans. So we'll just start at the top because it's very nice actually. It's a vertical algorithm, right? This goes from top to bottom, and we're actually writing it vertically in their system, so it has that very nice feature to it. How do I write an 8? a line and 3 dots, and the line goes below it, right? So it looks like that. How do I write a 2? 2 dots. I'm just going to write them out to the side for now. How do I write a 10? 2 lines. And how do I write a 12? 2 dots, 2 lines. And these are the correct symbols. I've written them spaced out just so that they're sort of showing up side by side of what numbers I came from. But if I were writing them all together, you'll notice that something sort of funny starts to look like it happens. Do you notice anything happening here that's a little funny? How many place values does it look like I have? 3. Do you see it? I'm supposed to have 4, but because there are no dots with this one, there's nothing that keeps the dots from the next place value up sort of separated from them in any natural fashion to verify that they really aren't a part of those 2 lines. And it is, again, one of those faults within the system itself, an inherent flaw, right, in notation. So that's unfortunate. It's correct, but it's unfortunate. Any questions on our Mayans? Okay. Romans are next. So where do you see Roman numerals used? Because this is the first 3 I don't think you probably see. Do you see Egyptian numeration systems anywhere? Mayans or Babylonians? Maybe you would if you're an archaeologist, right? But probably not in other things in your life. Roman numerals we see, though. Where have you seen Roman numerals used? In books, like titles or something like that, right, of a section. Sure. What else? On a clock. Mm-hmm. Where else? Some things with music. I didn't even know that. Very interesting. Okay. How about outlines? Have you ever done outlines with Roman numerals? That was all the big thing to do when I was in middle school and high school. Anyway, I don't even know if they still teach that. I have no idea. You guys, I know you're all girls, but does anybody see this used in sports? Some of y'all are in sports. I know you are. Where is this used in sports? Can you think of it? They usually use it for the Super Bowl. They'll designate the year of the Super Bowl with it. Did you not want to talk to me, Brooklyn?
No, I did. I was trying to think.
Where it was?
Yeah, I was like the Big 12, like, because they have like X.
That's true too. Yeah, Big 12 and Big 10 both use it. Mm-hmm. Yeah. So there's different places you see used it. You know, very interestingly enough, I have a brother-in-law who got married in Washington, D.C. area, and you see it on old buildings as well. They'll have it actually in Roman numerals, like the established date of the building. You'll see it on tombstones, older tombstones, which you see more in the east, right, than in Oklahoma. But so there are other places you'll see it used sort of at odd times as well. And I always forget to show this, so I'm going to actually show you my very last slide of this because this is somewhere I saw it in like real everyday life thing. This is a shirt at Kohl's, actually. Do you see it? The Roman numerals, MCMX. CVIII. We'll interpret what that is in a minute. I haven't even told you what all the Roman numerals values are, but it was on a shirt, and so I had to take a picture, right? Of course I did. All right, I got lots of slides to get back to now. All right, so our Roman numerals, you know what the first one is. What's its value? 1. You know what the V is. It's 5. You know the X, 10, and you might not know any beyond that because those are the ones we do see used the most. But let's just check. Any ideas what you think the L is? It's 50. Look at a pattern. What do you think C might be? 100. D? 500. And M? 1,000. Now, they have a couple of interesting properties. In fact, AK mentioned one of them last time when you were trying to tell me what to do on a different system. You were sort of guessing it might have worked the way the Romans did it. The first one you're probably familiar with. The second one you might not be. They have a property, it's a subtraction property. So they would never write a symbol more than 3 times in a row. So 3 times in a row is the max. So if they had a symbol they needed to write a fourth time, they would actually change the way they wrote it with this subtraction property. So they would place the larger symbol, the smaller symbol in front of the larger symbol, but you can only go one place value smaller to do this. So, for example, if you wanted to write 90, well, I don't write 9 tens, and I don't write 50 and 4 tens either, right? That's my problem, right? I don't write 4 symbols. So what I would actually do is I would write an X followed by a C. Because X is 10, and then C is 100. And since the 10 comes before the 100, it's subtracted. But you only go one place value smaller. So for example, if you wanted to write 99, man, it's really tempting to say, well, let's just go IC. That'd be great, right? Take 100 minus 1. But they don't do that. So if you just wrote that down, mark it out to remind yourself. They don't do it that way. They do it by place value. So they look at the 9 and the 90 first, and they think of this as 90 plus 9. And they do the 90, right? So that was XC, we already did that. And then they do the 9, and the 9 is IX. I made this comment in my college algebra class this morning, not about this, but I didn't make it up. Like, nobody asked me what my opinion was, right? I was not around when the Romans were doing this. So we have to do it the way they did it. And this is what they did. There's one more property they have. It's a very interesting one. If you take a look at these symbols, they don't go very large. I mean, 1,000 is big, but it's not like as big as some of the other numbers we've been dealing with in these other number systems. So what they do is they have a multiplication property as well. The multiplication property that they use is that if anything is bigger than what they would represent with the 1,000 symbols, like they can do 3,000, cool with that, right? 3 of those symbols, but once they get to 4,000, that's not going to work because they're not going to do it for their symbols. So what they do is they put a bar on the top of it. So for example, on this 9,000 here, they're breaking it apart by the thousands place, and they're going to write the symbol for 9. So what's the symbol for 9? IX. And then they put a bar on top of it, and that bar on top of that means times 1,000. So this is 9 times 1,000. And if they wanted it even bigger than the thousands place, they could do the millions, and they put a double bar on top of something. So if I wanted to do 9 million, it would look just like this, but it would have 2 bars on top of it. I'm not going to keep that there because it's not my number, but that's what you would do. Now, it's also interesting to note that if you have a number, it doesn't have to have a bar over everything. Like, let's say that it had 9,500. Well, we can do the IX for the 9,000, and then we can use our symbol for the 500, which is D. So you can intermix pieces that have a bar on top and pieces that don't. Or even pieces that have, double bars with single bars and that don't. All that can be intermixed. So if you think about, let me just jot this down as a reminder over here because I said it, right? So if we had 1,000, that's M. If we have 2,000, that's just 2 M's. If we have 3,000, that's 3 M's. And it's as soon as we hit 4,000 that we have the problem where we have to separate because I can't write 4 M's. So I write the number 4, which is IV with a bar. That's where this sort of takes effect. Okay, so we're going to do the same type of questions we did in the other systems where we ask what comes before, what comes after. So our value is MCMX. And I think it might be a good idea to remember that the slowest value, the smallest place value is still the ending part of the number. So it is X. So it's ending with the number 10, right? We're ending with 10. So if we want the number that comes before this, what do I have to do to the X? Make it a 9, which would look like what? Yeah. So it would still say the same as the MCM. And then I need to make the 10 become a 9. and a 9 in their system looks like IX. I don't need to know what the values are at the beginning. We'll deal with that in a minute, but just dealing with the ending value to change values one up and one down. So what Roman numeral then would come after that value? Not after our original value, MCMX. Yeah, you just add a 1 after it. So the MCMX, I need now, instead of it to be 10, I need it to be 11. And I make it bigger by putting the 1 after the X instead of before the X, which made it smaller. Okay, and now we're going to do actually breaking down the number in our system, the MCMX. So how much is the M worth? 1,000. C is, M is another 1,000, and then we already said X is 10. So what we're looking for is we're looking for any places where a smaller value comes before a larger one, and we have one, don't we? Yeah, right here. There's a smaller value, 100, coming before a larger value of 1,000. So that's a subtraction principle. So I'm going to write this out very carefully so that everybody's sure to see. Right here in the middle, I have 1,000 minus 100. You don't have to write that, but that's really what's going on. So 1,000 minus 100 is 900. So if I add that 900 to the 1,000 and to the 10, what do I get? Yeah, 1,910. Any questions on that? Okay. Let's go the other direction now. Now, we don't have to use a division algorithm on this, right? We had to do that when the place values were in like base 20 or base 10, base 20 or base 60. That's when we did that. We don't have a place value system with the Romans. We don't have that. There's a repeating, subtractions, or there's all these other sort of things going on, but it's not a place value system. So we're going to look at the numbers themselves and see where we need to put breaks in to see if we needed any bars, because this number's big, right? This number is 1,492,019. So at the very least, I know I need a break here. How do I know I do not need another break at the other comma before that? Any idea? So that's what we're not wanting to happen. So that's what I'm not going to need to put a bar, I don't need this, and to do what you just described. And the reason that I don't is because this number is smaller than 4,000. So it's the same thing that I was talking about over here. The number is 1,000 and some change, and I have a way to represent that. And if I put a bar on top of something that's already 1,000, I'm already going to get 1,000,000. So it's only necessary to put the line, that vertical line that I just broke it apart in that one place where the comma is the second comma. How do I write 1,492? What is 1,000? M. How do I get 400? It's subtraction, yeah.
Is it a C before a D?
Yeah, it's a C before a D. Good. So I do 100 minus the 5, or 500 minus 100. So the 100 goes in front of the 500. Right. So CD. That's my 400. How do I get a 90? X before a C. We've done that one a couple times now. And then how do I get a 2? 2 I's. And one bar on top of this multiplies all of it by 1,000, which puts me into the millions place. So an additional 2 bar doesn't end up being necessary. I'm not done. I still have the 19 that's at the end. How do I get 19? So remember, we're breaking it apart in place values, so I really have to do the 1 first. Yeah, X, and then, that looks funny, X, and then the 9 is IX. Any questions on that? Now I really want you to look at the Rayleigh Chapel clock. And we'll see what you see on Monday when you come back in, okay? All right, so there are a few other things in this section I meant to bring, and every time this sneaks up on me because it's like in the dead center of the lesson and I don't really think about where it shows up. I have blocks in my office that I will bring and I will show you, but this is actually talking about base 10 blocks. Base 10 blocks are often used in early elementary school, very, very common. And what they do is they're trying to teach children about place value, right? They're trying to teach them that a 2 in the tens place is worth more than a 2 in the ones place and so forth, that the 2 in the location it is matters, and that you can't combine certain things. So what we actually have is we have some blocks that show size to help with that. Money is another way you see that used. So a unit block is just one small little square, okay? A long is really, in our place value system, 10 of those tucked together. So imagine they were like Legos, right? And you attached 10 Legos all end to end, it would make one long Lego stick, right? And then a flat is taking those 10 long Lego sticks and then making that into sort of a larger rectangular square, right? It's bigger than it was before. So that's a flat. And then a block three-dimensionalizes all of that. So for a block, it ends up looking something like this. Sorry, it makes it look like my block is smaller than my flat. We'll make that different. I can adjust that. Look, that's more believable now. That one too. Much better ratios. Okay, so it's additionally adding on pieces. So if I have one unit and I have one block, nobody's going to try and add those things together and say somehow I have two, because one is significantly different in size than the other one. Now, I mentioned what happens in base 10, right? So I have base 10 blocks in my office. They're red. They're plastic. I'll bring them next time, provided I can remember. But what you'll see is that if you attach these all in the way that I've said them, they're base 10 blocks, which means everything's based upon a power of 10. So this is worth 1, and these are 10 of them stuck together, so this is worth 10. And this is a 10 by 10, so it's worth 100, and this is 10 by 10 by 10, so it's worth 1,000, right? I mean, that's the visual imagery that they're trying to create for us. But that's specific to the fact that they are base 10 blocks. We could have other base system blocks, and we could actually do the same sort of thing. Now, in my office, I also have base 3 blocks. I'll bring those too. And they do the same thing. They just don't have them as length 10 everywhere. It's length 3. So if you imagine, and we did this with base 8, right? So over here, a unit's still 1. That doesn't change anything. But what changes is that when I string the units together to make a long, I only string them 8 long. So when this says in base 8, how much would a unit, long, flat, and block be worth? Well, unit's always worth 1. And then if a long is worth 8, because it's 8 long, what do you suppose a flat would be worth? 64. And what would I have to do to get a block in base 8?
Cube 8.
Yeah, I need to cube 8. So somebody cube 8 for us and let me know what you get. 512. Yeah. So this one's my unit. This one is my long, my flat, and my block. And they're all just powers of 8, right? Absolutely. So if we actually considered this number 237, and I won't say 237 because when I say 200, it means I have 2 hundreds, but I don't. I have 2 flats, and a flat's worth 64. So I can't really say 200, so I'm just going to say 237. Okay? So I have a 2 flat, and a flat's worth 64. I have 3 longs, and longs are each worth 8. And then I have 7 left over. So imagine somebody comes in and they have their Legos assembled all like this. And in essence, what we're really doing is we're just breaking the Legos all apart and we're counting the individual units. Okay, so there was these two flats, they were 64 each, and I busted them all apart, and now they're each actually 64 pieces. So I'm counting the pieces. So what is 2 times 64? What is it, 128? 3 times 8, of course, 24, and then 7 more. What would be my total? 159. So there's 159 individual units. This question that I just did in Part B is equivalent to asking what 237 base 8 is equivalent to in base 10. Okay? So we're turning it all into base 10 because that's our familiar to us number system. That's the idea. Well, that's just base 8. So what would we be doing if we had other bases? So let's actually take a look at 3 other number systems, not because there's anything special about these 3, but because I think that showing you 3 of them is enough to give you a general idea about how to do any base number system. Okay? Now, before I go too much further, there's a couple things I want to say. One is the fact that no, you're probably not going to be teaching the 4th grader to do base 8 addition. I get that. Okay? That's not the point of this lesson. It's not the point of using the bases in the other systems. The point of it is to put yourself in a position that makes you feel a little bit uncomfortable. You're uber familiar with addition and subtraction in base 10. It is no big deal. You've been doing it for a dozen years or more, right? Which 1st graders haven't. So part of what we're doing with the other bases is to put ourselves in a position of being a little bit uncomfortable and remember that what's familiar to you is not always familiar to your kids, right? The other thing is that there are other base systems that we use and we don't think about them all the time every day. For example, our clock. Our clock is very interesting. It is not a base 10 clock because there's not 100 minutes in an hour, right? We don't have that, right? And there's not 100 seconds in a minute. It's not a base 10 clock or tens of those things. Not only that, but there's not even 10 hours in a day, right? It's weird. We have this weird base 60, base 12 weird thing going on with our clocks. Another place that you see different bases used is you see different bases used when you work within some of our like measurement systems. Like think about inches to feet. It's 12. Why? I don't know why, but it is, right? It's this weird base 12 thing going on. If you work in computers, computers are done in base 2. Or, that's a base 2 number system, or they're done in hexadecimal, which is base 16. For computer programming, oh yeah. So there's other base systems going on in our world too. We don't think about them all that frequently. In fact, we use the clock all the time and we still don't think about it. Isn't that interesting? We just get familiar with it and accustomed to it and we just move on. All right, so we're going to look at 3 base systems. They are randomly chosen, truly. But base 3. Now, first of all, I mentioned last time when we talked about base 10 that there's no numeral for 10. We have a 10. It's a 1 and a 0, but it's actually 2 numerals, right? Numerals are single digits, so there is no 10 in base 10. So the reason I'm mentioning it now is because there will be no 3 in base 3, no 7 in base 7, and no 12 in base 12. They won't exist. It stops 1 before then. So if we have base 3, just like base 10 we had 10 numerals, base 3 has 3 numerals. It's just that there's 0, 1, and 2. There are no more bigger numerals in base 3. Okay, so this becomes the same question that we were looking at in our other number systems, and the Egyptians and the Babylonians. Well, what do you do then when you get something bigger? How do I represent it if I'm a base 3, Martian or something? I don't know. What do I do if I'm one of those peoples? Well, you have to go to 2 digits because that's what we do when we run out of digits in our system, right? What comes after 9? Well, we don't just stop there. We have a 2-digit number, and in the 2-digit number we call it 10, but it's a 1 followed by a 0, right? So you do the same thing inside of base 3. When you run out of single digits, which we have now, 0, 1, 2, you go to a 2-digit number, and the smallest 2-digit number is the number 1, 0. It's not 10, it's 1, 0. And what do you suppose comes after 1, 0? Before 1, 2. 1, 1, and then 1, 2. But there's no 1, 3 because there's no 3. So what would come after 1, 2? 2, 0. We're going to go a little further with this one. What's after 2, 0? 2, 1. 2, 2. Ooh, now what? I need 3 digits, right? I'm out of digits for a 2-digit number. So then it becomes the digits 1, 0, 0. And of course this continues indefinitely, right? I'm not continuing this any further. But I wanted you to see that you just end up getting to the 3 digits and the 4 digits. It all happens so much faster because you run out of digits so much sooner. Okay? Let's try it with base 7. It starts with 0. What is my biggest digit in base 7? 6. Right. So 0, 1, 2, 3, 4, 5, 6. And then what's going to come after 6? 1, 0. And then this is going to go up to, what's my highest 1 something? 1, 6, right? And it will keep going from there. What would be my biggest 2-digit number in base 7? 6, 6. Yeah, it would be, right? It's just the largest digit doubled, right? Our largest 2-digit number is 99 because it's our largest digit doubled. Okay? Okay, so what about base 12 makes it different than the others?
It's already got 2.
Yeah, and so I'm going to say what you just said, but in a little bit differently. It's bigger than my base that I actually already own, right? I own base 10. You all own it too. You already have that system, and we were taking away digits in base 3 and base 7. But somehow that's not going to work if I'm going to be working in base 12 because I need additional digits, right? I'm supposed to have 12 digits, and I can't have the digits 1, 0 because that's a 2-digit number. I need another single digit. So if you took contemporary math online with me, this is something that's different in this book than that one. Just a warning. And I know Dana did. She's not here today. But what our book does is they do the digits up to 9. Okay? So that's 10 digits. But I need a digit for an 11, and I need a digit, I needed a digit for an 10, and I need a digit for an 11, right? I need a 10, and I need an 11. So what your book does is they do T for 10 and E for 11. Other resources will go to the alphabet, and they'll use A for 10, B for 11. I like that better because I think it generalizes a little bit better. Just so you know what would happen if it were in base 13, because you can't just use like a T for 13. Now, they do use a W, but I don't think your book goes any higher than base 13, just so you know. So I have T, and then I have E, and then I run out of digits again, and so I go to 1, 0. All the way up to 1, 9. And then what do you suppose comes after 1, 9? It's kind of funny. 1 T. And then 1 E. Because those are the next single digits in that place value system. And then I would go to 2, 0. Well, what is my biggest... I already did this one up here, didn't write it down. 6, 6 was my biggest 2-digit number there. What is my biggest 2-digit number in base 12? Say it again. Nope, not 90. Is that what you said? 9E, you're really close. EE. Yeah, it's EE. So I have 2 digits, and it's the biggest digit that I own in that place value, or in that value system. EE. And then I would go to 1, 0, 0, just like in the other systems. Kind of different. Okay. Okay, so what I did when I was doing numeration systems is after I sort of established what their system was, we looked at what comes before, what comes after, right? We can do the same thing with these base systems. What comes before, what comes after. Typically speaking, one's pretty straightforward and easy, and one's not. That's why they're asking the question the way they are. So here's 1-4. Notice the word that's written as a subscript. That's what lets me know what place value system I'm in. Without that word there, the assumption is that you're in base 10, just like you've been working in, the rest of your life. So if you're not in base 10, you definitely need to write what the word is that you're in the base system down beside it. All right, so what would come before 1-4? Somebody said it. 1-3. 1-3, again, make sure you write down base 5. 1-3, base 5. So what then would come after 1-4? It's not 1-5. 2-0. So 1-5 won't work because there's no 5s in base 5. So I've run out of digits, essentially, when I get to 1-4. So I have to increase the next digit over, which is my 1 in this case, so it becomes a 2. So this is 2-0 base 5. So this is the number before and the number after 1-4 in base 5. So we're going to do the same thing in base 12. So we have T00. It looks like a 2. 12. Okay, on this one, the easy one's the one that comes after. What comes after T00? T01. Remember, we only change the last digit. That's our goal, is to only change or affect the last digit when we can. So this is T01 base 12. It's the number that comes before that's harder. Any ideas what comes before T00? It'll start with a 9. Very good. Because the number that's before a T is a 9. Right? Look back over here. What came before T? 9. Then what? Let me do a different example. Pause for a second. Put back on your base 10 hat. Let's say you had the number 700. Our base 10 system, no problem. So what Kayla already did is she said, well, the 7 at the beginning, our T, has to go down by 1. So we'd make it a 6, right? 7 turns to 6. That's where we are in this problem. What do we do with those 0 zeros when we're looking for the number before 700? What numbers are they? They're 9s, right? This is just 699. Everybody good? I'm not trying to trip you up. I'm just trying to make you think about what you're doing when you do that. It's 699. That's the number that comes before 700. These numbers here at the end are the biggest value in base 10. It's the biggest digit, right? So I decreased that first one, and then I used the biggest digit in base 10. So I need to do the same thing up here for my T00. T became a 9. What is my biggest value in base 10? E. So this is E, E. And I'm out of space, so let me shift this a little bit. It needs to have the word 12 written down next to it. 9E, base 12. A little uncomfortable? See, you had no problem telling me that before the 700 came 699, right? No problem. I don't think that your first graders would have no problem with that. It wouldn't be that easy, right? Just like figuring out that 9EE came before T00 was for you. All right, so we're going to look at a little bit of converting before we end today. We won't finish this lesson. which is exciting, right? Because there won't be homework due on Monday. It will be due Wednesday, and I think we will actually end up then having homework due Friday as well, just prefacing you on preparing, right? But yeah, this won't be due. You could start working on it. That would probably be a good idea. All right, so this is actually having us do base conversions. So we are going to convert in this time from our whatever base we have, okay, base 2, base 7, base 15, base whatever base it is, into base 10. And what we do is we put the numerals into expanded form, and then we multiply out the expanded form. So let's see what that looks like. Expanded form means recognizing what each of these are actually worth in that place value system. For example, if we're working in base 2, then our place values have bases of 2, namely 2 to the 0, 2 to the 1, 2 squared, 2 cubed. That's what they're worth. So if you're thinking about converting this, you're going to take the number that's in that place value, a 1, and you're going to write it as a multiplication factor times 2 cubed. That's expanding the bases. I'm going to write the next two out even though I recognize that they're zeros just to set you a pattern. Whatever number's next, you'd put that number, and it'd be times 2 squared. That same thing is another 0 times 2 to the first. And the last number is a 1 times 2 to the 0. And then you're going to figure out what each of those powers of 2 are. What's 2 cubed? 8, so I have 8 times 1 here. I know that this is a 0 in the middle and a 0 here, but it would have been 2 squared, which is 4, and 2 to the 1, which is 2. What is 2 to the 0? It's 1. Anything to the 0 power is 1. It always ends with a 1. I mean to say this value at the end is always times 1. All right, so 8 plus 0 plus 0 plus 1 makes a big old whopping 9. Oh, look at there. The T00 showed back up, didn't it? Okay. But it's base 12, right? So I won't write them all out in longhand this time. But this is the 1's place and the 12's place. And what's the next value? What place value am I in? 12 squared, right? It's 12 squared. So I have a t, I'll leave it as t right now, times 12 squared, plus 0 times 12, plus 0 times 1. But what's t? T is 10. 10, so I have 10 times 12 squared is 144. And these are both zeros at the end. So what is 10 times 144? Yeah, 1,440. Okay, so when we're working from another system into ours, we multiply. Okay? We'll pause there today. There's one more piece for us to do to go the other direction, and we will end with that on Monday. So on Monday, we will finish this lesson. We will start 3.2, and we will do group work from 3.1 as well. All right?